Hi everyone. Thanks so much for dialing into this week's Covideo webinar and taking the time to listen to my talk about the multi-scale characterization of Australia's deepest drill hole. Where is my, oh, there we are. Okay, this would have been my preferred name for the talk, but I decided against it at the last minute before I sent it to Pat. Characterization of this magnificent beast really wouldn't have been possible without a really big team committed to the cause. So thank you all, and thank you to Northern Star and DDH1 for getting it out of the ground. Before I go any further, I'd like to acknowledge the traditional owners of the land we're all meeting on today, particularly the Whadjuk people of the Noongar Nation, where I'm located at here in Fremantle, and pay my respects to their elders past, present and emerging. For those of you who are unfamiliar with the Jundee Gold Camp, like many gold camps in Western Australia, it's an Archaean greenstone-hosted gold deposit. Production at Jundee commenced in 1995 with the Great Central Mines, and then it changed hands twice before Newmont Mining took over in 2002. Just after the camp's 6 millionth ounce had been poured in 2012, Newmont Mining scheduled to close the mine in 2013. Before this happened, Northern Star struck a fabulous deal with Newmont and acquired Jundee in 2014. Northern Star have since extended the mine life, I think at least 10 years, maybe more. So kudos to you, Northern Star. And as you can see from these hand samples, thanks Michelle, Jundee has some spectacular grades. So where in the world are we? Where is Jundee? So Jundee is located in the northern Yilgarn Craton in Western Australia, in the very famous Kalgoorlie terrain, but it's over 500 metres from the Kalgoorlie goldfields. The Yandal Belt is adjacent to the historical Wiluna Gold Camp, and Jundee is located about 45 kilometres northeast from the Wiluna Gold Camp. Regionally speaking, the Archaean Yandal Greenstone Belt comprises of banded iron formation, ultramafic and mafic volcanics, which you can see there, intermediate to felsic volcanics with variable sedimentary units throughout. Early shear zones form the Greenstone Belt margins, you can see here, and trend north-northwest and north-south in the belt generally. The basaltic units in the Yandal Greenstone Belt vary from tholeiitic to high magnesium compositions and are commonly pillowed with sulfide-rich interflow shale layers. The basalts are intruded by synmagmatic dolerite sills. There are many gold deposits dotted along the Yandal Greenstone Belt. You can see Jundee at the top here. Others include Bronzewing down here and Darlow, actually, which you can't see because it sits at the bottom, but didn't extend it. It should have gone a bit further. Okay, so locally, the Jundee stratigraphy consists of basalt sediment sequences that have been intruded by multiple dolerites. So you can see here the Fisher Basalt, the Lyons Basalt, intruded here by the Hughes and Barton and Lyon dolerites and the Campion dolerite up here. These stratigraphic units are later intruded by lamprifiers pretty much everywhere. Porphyries, granodiorites, granites, and further Proterozoic dolerites. The gold lodes at Jundee are hosted in multiple sets of north-south and moderately west-northwest trending faults with extremely intense but narrow visible alteration halos. Based on the alteration assemblages discussed in this presentation, the assumed metamorphic grade at Jundee ranges between greenschist and amphibolite facies. Excuse me. How did the drilling of this giant drill hole come about? Well, in 2018, the Jundee exploration team defined a large mineralized corridor of the Zodiac Discovery near the main mine. They shot a 3D seismic survey in the area, and then to help validate this really cool seismic data set, the team decided to drill a very long 3,217 meter diamond drill hole. I really feel sorry for the offsiders pulling that thing out. So this is all really exciting because this super long drill hole traverses the entire mine stratigraphy and the intersected mineralization. A previous study at CSIRO looked at high-grade ore samples taken from the main mine, and the results suggested that lithological boundaries in the mine stratigraphy exert a mechanical control on the extremely high-grade ore, Therefore, constraining the mind's stratigraphy, particularly those mafic units, is important for future exploration. And scientifically speaking, looking at over 3 kilometers of stratigraphy from a world-class gold camp is pretty awesome, particularly considering that the literature is limited. So, our workflow started out with acquisition of continuous XRF data with the mineralized core scanning system and finished with the TIMA SEM. We acquired portable XRF on each of the TIMA rounds to constrain the lithogeochemistry, as well as compare the data with the mineralized for acquiring semi-quantitative portable XRF data on site. In addition to these data sets, we scanned the core with a high-logger 3 and mapped some core samples with the Maya mapper. But we'll leave those for another day when we've digested the data from the original project, because there is a lot. So, starting off with the mineralized, soon after the 27 or so pallets of core turned up at the CSIRO site in Kensington, which I can tell you is a lot of core even for the largest of core yards, and we really don't have one. We scanned the entire drill hole with a mineralized core scanner, which operates on whole trays of core at a time, providing non-destructive. For this study, we binned the measurements to 1 meter intervals, and for each of these 1 meter intervals, we get elemental concentrations with an uncertainty value. The mineralized core scanner also takes high resolution photos of each tray, so which you can later analyze for structural and core quality analysis. After the mineralizing was complete, we used the mineralized data with support of the lithology logging and the gold assay to inform the TIMA SEM sampling. We sampled systematically across each of the lithostratigraphic units, and depending on the nature of each unit, we reduced or increased the sampling density. For example, across the drill hole's beautiful pillow basalt, we reduced the sampling density. So it was like maybe 1 every 15 to 20 meters, but across, and sometimes it could have been every meter. Portable XRF measurements were then taken on each of the TIMA mounts, and as mentioned, and also we took additional infill measurements where we didn't take as many TIMA mounts. So from those little half cores, cylindrical rounds were drilled out, and the rounds were either cut down or left whole, or cut down and left whole, or resin mounted and polished to a 0.5 micron diamond suspension finish. That's where the little, this is not from Jundee, but the little rounds drilled out here, you can either leave it like that and polish one side, or you can take off a little wafer and pop it into the resin mount, which actually is a much better process in hindsight, but anyway. So after the rounds are polished, thank you, Tina and Katie. You are the dream team. Automated mineralogy was conducted on the 400 plus rounds using the TESSCAN integrated mineral analyzer, or TIMA scanning electron microscope, or TIMI, as he's very fondly known in the building. We ran these samples at a step size of 10 microns, which took about 2 hours per sample. Each 10 micron pixel has a unique X-ray spectrum, which is dependent on the composition of the minerals present in that little area. The TIMA software then uses a spectrum matching library to assign a mineral to each of those 10 micron pixels. The mineral library used in this project was tailored specifically for this set and is built on 10 plus years work of CSIRO that CSIRO was done using SEM based techniques in gold systems. When the TIMA is operating in its modal mineralogy mode, it produces mineral abundance in volume %, which can be exported as a CSV along with the mineral phase and BSC panorama PNG images. As you can see there on the left, there's a little PNG, which is super awesome. The phase panoramas are really integral to interpreting the key alteration mineral assemblages and underpinning the textural relationships present in each sample. Okay, so now we've got the method sorted, we'll move on to the results. So before we get into it, I'll give you a quick summary. Some of the key pieces of information we can get from the geochemical data are as follows. So when systems like Jundee undergo metamorphic and alteration events. It's not always possible to identify the primary lithologies. So using XRF data, the felsic and mafic igneous sequences can be distinguished by looking at the immobile elements, such as titanium, zirconium, and chromium. Even after these metamorphic and hydrothermal alteration events, you can separate the units. The added advantage of having continuous high-density data along the drill hole means that we can further differentiate by looking at the spatial patterns in chemistry and the lithological logging. Plotting the zirconium, chromium, and titanium data on a ternary diagram allows you to start separating the mafic and felsic rock types, as well as identifying igneous evolution or fractionation within these rock types. The trends identified in the mineralized data can be understood by considering the original igneous evolution of the greenstones. So considering the most primitive mafic units, looking down at the bottom left-hand corner on the chrome, we can, just to the right of the ultramafic units, mafic units here are chrome-rich as silicate minerals such as clinopyroxene, orthopyroxene, plagioclase, and olivine will crystallize first, which preferentially incorporate chromium. So as the magma continues to solidify, the chrome content decreases and the trend moves towards the right. During crystallization of these mafic units, there's no change in zirconium or titanium, as these elements are incorporated into the silicates at the same rate. However, the zirconium-titanium trend moving up to the top here, but you can see in the most fractionated dolerites, signifies a depletion of chromium and crystallization of titanium and zirconium bearing mineral phases. We can take advantage of the chrome data variation when looking at our mafic units spatially down the drill hole. So, while the ternary is really cool, the continuous XRF data allows us to gain spatial context and actually see the fractionation patterns in each of the greenstones in real life. Comparing the downhole chrome values against the lithology logging, you can see that it matches really well, which is a credit to the site geos. In addition to seeing the fractionation patterns, we can get insights into the effects of fracturing, faulting, and alteration, as well as the orientation of the mafic units when integrating the geochemistry data with the logging. Considering the sheer size of this data set, I'm only going to discuss the mafic units in the rest of this section because there's just so many. And I'll very generally describe the patterns in the dolerites using established models of igneous differentiation, where crystallization from both the top and bottom leads to basal and top zones that are relatively rich in plagioclase, and those basal zones are then overlain by chrome-rich cumulates of olivine or orthopyroxene-rich lithologies, then final zone of pyroxene plagioclase rocks. So zoning in. The uppermost part of the stratigraphy, Cambrian dolerite, so it's really low in chrome. You can see down here that it's just pretty much on zero. This unit in the most evolved section of the ternary. It also has a titanium and zirconium enrichment at the top, which you have to take my word for, but it's missing the more primitive compositions towards its base that should be chrome-rich. Assuming the conventional tholeiitic magma formed this dolerite, we'd need to see that sequence of cumulates to complement the dolerite, but it doesn't exist, at least in this part of the stratigraphy or snapshot. Evenly distributed chrome across this D shape here in the Lyons dolerite to the right of the Lyons Basalt could actually be the chrome cumulate little tail for the Cambrian dolerite, but it's a big basalt in between, 100 meters of basalt, so it's pretty unclear as to how these two would link up, but we would need more drilling to confirm it. Can you do that mute, Ryan? All right, moving on in this stratigraphy, the Lyons Basalt. So it's the first part is here. We can see the little purple intrusions, the lamprifiers. So two basalts, second one down here. They're very, very, very different texturally and geochemically. So the upper part is a sequence of lava flows and is heavily intruded by lamprifiers. The highest chrome values are towards the center. The lower part, which is beneath the Lyons dolerite, is a sequence of pillow basalts that are uniform and really distinct in composition. The chrome is really low, and therefore, and also it has a higher zirconium titanium ratio than the other basalts, meaning they're probably more fractionated too. Moving along, this is the exciting bit. The third dolerite in the sequence, the Hughes dolerite, has an extremely high chromium base. You can see that up there. It's actually like amongst the highest values we've seen in the core, but within 30 meters, it decreases to nothing. If you look closely at the high chrome peaks, you can see there's more than one. The unit appears to be repeated by faulting. In addition to the chrome anomaly in the sediments, between the dolerites down here, it's ultra silicified, and which both of those things are consistent with faulting. The Barton dolerite underneath here is a typical S shape in terms of its chrome chemistry, where the cumulates are most focused in the bottom half of the flow. Moving on to the final section of the stratigraphy, the fissure basalt and the Plover-Bore komatiite. Similarly to the Hughes and Barton dolerites, the sequence becomes more chrome-rich down section and appears to be repeated. The proposed location of this fault would sit at around 2,200 meters. And similarly to the other proposed fault zone, it's intruded by granite and has some mineralization. However, it is also possible that the two sequences here are just separate flows. The chemistries are similar, but there's nothing really definitive linking them together as there is between the Hughes dolerites. Each section of this basalt komatiite base, and they become more evolved up section. The sequences are almost identical in thickness and geochemical expression. The implications for this proposed large fault, well, the implications this proposed large fault has on the Gold Camp is unknown at this point, but it's good food for thought. Another little thing worth mentioning is that you can see here the little S shape in the fissure basalt. This is likely a boundary and within the greater fissure basalt unit. It's not repeated in the bottom down here because I reckon the intrusions might have ruined any chance of preservation if it is in fact a repeated unit. In the upper part, however, here we're seeing really pervasively altered rocks, which could be indicative of an important fluid pathway, but we'll come back to this. Okay, in summary, the continuous XRF can be a really useful technique to underpin evolution and characteristics of thick mafic bodies, particularly the dolerites. Intrusions are linked to weak spots in the stratigraphy, such as fault zones, flow boundaries, or lithological boundaries. We have a proposed fault zone within the Hughes dolerite, plus or minus a fault in the fissure basalt, but we'll leave that one for now. All right, let's look at the alteration mineralogy. So this slide is a very high-level summary of the methods surrounding the TIMA SEM technique, which builds on 10+ years of mapping deposits to camp scale alteration patterns with the main aim of understanding the fluids that drive the key reactions. Most of our recent work with utilizing this method as an exploration tool was within MREWA 494 project. The results for the project were officially released this year, and you can find them online on MREWA's website, or if you're interested, you can email me. What we've learned is that mapping minerals combined with an understanding of the important textural relationships can help us identify potential fluid pathways leading us to gold. Unraveling that textual information, though, starts with the alteration paragenesis, and understanding the alteration paragenesis enables us to infer conditions surrounding metamorphism, hydrothermal alteration, and the mineralization events. My colleague Adam Barth will talk in more detail in our next webinar about a new, faster and cheaper analytical method we're testing to map these minerals across gold camps in Western Australia. So make sure you tune into that one. Just to give you a bit more context and just how much information we can harness from each of these 25mm rounds. You can see the red box at around the 600-meter mark here in the stratigraphy. This interval contains less samples across the interval than on average across the whole hole, but you can start to see the level of the detail involved and get a feeling of the size of the data set with over 400 samples across this entire drill core. I'm going to come back to the mineral zoning patterns and some of the interesting findings, but for now we'll continue getting the alteration paragenesis sorted out. So after I stared at 400 rounds for what felt like an eternity, the alteration paragenesis for each of the rock types just fell out. It was like magic. Not really. I'm going to focus only on the mafic units, which are the dolerites and the basalts, as I'm sure you've got more to do this afternoon. In summary, the stratigraphy in this drill hole has encountered 3 stages of hydrothermal alteration, these 3 here, on top of the metamorphic event. I'll describe how we came to these conclusions in the upcoming slides. If you've noticed the mention of amphibolite facies here, just forget that for now. I'll come back to it. I'm only going to describe the greenschist facies assemblages as they are most important with respect to mineralization. So, starting at the beginning, this sample is from the Campion dolerite, and the protolith assemblages would have likely consisted of orthopyroxene, clinopyroxene, plagioclase, quartz, and titanomagnetite. This sample is great for observing some of the early metamorphic history, as some of those original textures from the dolerite are still intact, like this little titanomagnetite friend. And there is really little alteration from the later hydrothermal stages. Greenschist facies mineral assemblages are characterized by chlorite, albite or sodium feldspar, epidote, actinolite, quartz, and titanite. You can see this mineral assemblage present throughout the sample, and you can see evidence for these reactions taking place, such as the composition change of plagioclase minerals from the calcic end member anorthite to the sodic end member albite. It's in here, and you can still see the kind of like little shapes. So leucoxene, this purple thing, that's a product of a titanomagnetite, which is present in the dolerite protolith. It's pretty consistent across the dolerites intersected in this drill hole. You can see from this figure, well, you can't see from this figure, sorry. One of the really interesting things we noticed here is that the metamorphism was incomplete, meaning that there are partially altered protolith minerals, such as pyroxene and anorthite. What implications this has on the greater mineralizing system is still up for debate. The first stage of hydrothermal alteration, or stage 2A, as I've got it in the paragenesis, is characterized by overprinting of potassium-rich minerals, such as muscovite and potassium feldspar, and biotite at depth, but we'll come back to that. There's also been enrichment in sulfur and quartz as compared to the metamorphic assemblage. You can see the feldspars have altered here quite nicely to muscovite, and we expect this has occurred by a potassium-rich, possibly acidic fluid. So the stable assemblage for stage 2A is muscovite, albite, K-spar with some quartz and calcite. And with these minerals as a stable assemblage, we would expect the temperature of this alteration event to be somewhere between 320 and 400 degrees, which is quite a large gap. But if you want to know how we came to this conclusion, I can show you a little phase diagram at the end. So the second hydrothermal alteration event observed in the drill hole, stage 2B, produces an alteration assemblage that suggests the fluids are more likely alkaline than more alkaline than the previous hydrothermal event, with variable CO2 and sulfur concentration. This is the most important paragenetic stage described because it's linked with gold mineralization. The alteration assemblages of stage 2B commonly contain chlorite, mostly clinochlor, but some chamosite, calcite, pyrite, titanite, albite, and quartz. You're able to see the stage 2B chlorite and calcite overprinting the stage 2A assemblage in this figure. So although the stage 2A muscovite, albite, quartz assemblage were consumed in this stage, reactions are only complete in the strongest altered parts of the mineral system. Equilibrium modeling and the in the golden mile dolerite shows that this assemblage is stable below 420 degrees. So putting this stage at an upper temperature limit similar to the stage before, about 20 degrees higher at 420. So stabilizing titanite and not rutile at 420 degrees in a gold zone is uncommon as compared to other camps we've studied in Western Australia. We'll come back to this. Just quickly before we go back to the gold zone, the final alteration assemblage, which postdates the gold, stage 2C, is characterized by mineral assemblages that are indicative of a lower temperature and lower carbon dioxide fluid. The assemblage is dominated by clinozoisite, epidote, and quartz. Plus or minus K-spar, prehnite, and pompiliite. I forgot about those. Okay. All right, back to the action. This figure is from the high gold intercept in the drill hole. Stable phases in the gold zone are chlorite, calcite, pyrite, tourmaline, titanite, sometimes a bit of scheelite, and background albite and quartz. The temperature constraints of 420 degrees that I mentioned earlier, paired with the stability of titanite, predicts a lower XCO2 value, which, remembering XCO2 is a ratio of carbon dioxide to water in a fluid. So at low values, we've got a lot more water activity. Titanite can also be stable at higher XCO2 values, so pretty much where there's all CO2 in the fluid. But these systems are much, much hotter, and we would see phases like biotite and anorthite, as well as ilmenite, which is certainly not the case here. The most noticeable difference between the earlier stage 2B figure is really how pervasive the alteration is here. But this pervasive alteration is not limited to the gold zone, as I mentioned earlier in the lithostratigraphy. So around 50 meters below our gold zone, which is our gold zone is here, we can see around 40 meters of equally pervasively altered but unmineralized rocks. It has all of the visual markers of a well-endowed mineralized zone except the gold. So why didn't it precipitate here? Are there any subtle differences between the two? Taking a look at the blue box around the unmineralized zone, the most obvious subtle difference is rutile stability. So rutile is here, and we've got a little peak in the box, and we've completely lost titanite. So rutile stability within this given temperature means that we are likely in a higher XCO2 zone, so more CO2 in the fluid than where we find the gold. Results from our previous work in the M494 project demonstrated that the gold zone at the Wiluna Camp actually has a similar alteration assemblage to this unmineralized zone at Jundee, with rutile as a stable titanium phase. However, that is not true for the gold zone here. Rutile zones in other Archaean gold camps have been associated with gold mineralization too. For example, St Ives and Kundana. Jundee sits somewhere between Wiluna and the Kundana camp temperature-wise, but it's really quite different. Well, at least for the sample we've analysed in this drill hole. Jundee is known for being very nuggety and having high-grade lodes, and similar to faults, gold lodes can vary along strike. So understanding how the minerals in this unmineralized zone here change along strike is a really important question. One last thing to mention here, the blue dots on the left are titanium values from the portable XRF, which are taken directly on the TIMA mounts. You can see the titanium values alone aren't able to give you any insights into the changes in the titanium phases. And this is a great example of why mapping minerals is much more informative than just analysing bulk compositions. So I thought I'd better show you a picture of the pervasively altered stage 2B that has no gold. So the minerals in blue have changed from the gold zone. Another subtle difference here is the presence of arsenopyrite. Arsenic is really often a pathfinder element in many gold systems, but in this drill hole, and from my understanding in other parts of the camp, it'll get you close-ish, but not quite there. In the M494 project that I was talking about, we demonstrated that the fugacity of CO2 and pH-sensitive sulfate carbonate, and sulfide mineralogy, combined with important textural information, was able to identify oxidized, CO2-rich, and potentially alkaline fluid pathways that can lead us to gold. If by chance this unmineralized, highly altered zone happened to be an important fluid pathway, and we're assuming the same hypothesis formed in previous projects, a possible reason there's no gold here is because the oxidized alkaline gold transporting fluid needs to evolve first, so it becomes more reduced and neutral in pH before gold precipitation will be favored. Now, of course, this hypothesis needs to be tested at Jundee, but we have a good starting point. From results in the previous work, we found that anhydrite, which is a calcium sulfate mineral, can also signify some of these oxidized pathways. In some camps, anhydrite's footprint has been shown to extend a lot further away from these highly altered proximal to gold zones. And the amount of anhydrite we've seen in other camps is highly variable too, sometimes 0.01% in the sample. So now I know what you're thinking. Does anhydrite exist at Jundee? And the short answer is yes, in varying quantities. But we would really need to take a closer look with an SEM in order to link it paragenetically to stage 2B. At the moment, it's unclear if it's linked or if it's associated with the later stage 2C. But if we were able to link the anhydrite paragenetically to the gold event, we'd potentially be highlighting a pathway of interest. However, understanding the role that fluids play in transporting precipitating gold is incredibly complex, and there are many, many factors that affect mineralizing conditions. So it's tricky, but the hypothesis is really exciting nonetheless. All right, so before we jump into the final section, in summary, the mineral zoning combined with the texture uncover important information leading us to gold. Jundee is known for having very nuggety high-grade lodes, and understanding how the alteration minerals in that unmineralized zone, how they change along stracks, really important. And the question, how similar or different is Jundee to other camps, and particularly Wiluna, but also parts of the Kundana camp? And can we use anhydrite as an indicator for oxidized fluid pathways, as we've done elsewhere? Okay, amphibolite facies coming up. So you might have remembered the amphibolite facies in my earlier paragenesis slide. We focused on the greenschist assemblages as they're most important for mineralization at Jundee. However, this drill hole is just so long. We kept finding more and more interesting things to look at. So as I've been saying, for mafic protolith, the greenschist facies assemblies is chlorite, albite, episode, actinolite, quartz, and titanite. But if you look below 2,050 meters, pretty much at the beginning of the upper Plover-Bore komatiite, we start to lose actinolite and chlorite at depth. So you can see here is pretty much gone. And it's starting to look like our metamorphic event has been upgraded. However, I'll show you some of the textural relationships and let you decide. So above that 2,050 meter mark, we see the greenschist facies assemblage. Cheating a bit because this is the very, very, very top sample, but it's a perfect example for showing the textures. You can see alteration minerals is quite static. The original texture there's no plastic deformation, and as you go down, you do get a little bit more fold, but the assemblages are still consistent. Below 2,050 meters, we start to see the disappearance of chlorite and the appearance of the aluminous amphibole hornblende, plus calcium feldspars, somewhere between anorthite and antizine, and quartz. Titanite is completely wiped, well, not completely, almost wiped out by ilmenite, and we start to see pyrrhotite forming there as opposed to pyrite. The dead giveaway, although before any of that, is the textures. The strong foliation and plastic deformation of the feldspars across the entire fissure basalt is a dead giveaway. Okay, in summary, we have greenschist rocks from 2,050 meters up, and amphibolite facies pretty much below. This part down here, the questions is that considering it's really similar to bronzewing, like, can we link these systems, and what implications does this really high temperature or higher temperature zone have for the greater camp and the mineralizing system, and also like links to other parts in the belt? Okay, so the take-home messages. Sorry, the slide is busy, but I couldn't really shrink it down. So first one, the greater camp to belt scale architecture. Do we have any other evidence for repeated sequences in the camp, particularly within the Hughes dolerite? And what new insights can these structures tell us about the deposit? The metamorphic grade below the fault zone, what does that tell us about the greater camp, and does it have any links to bronzewing, for example, or deposits down the line that are also equally higher temperature? 2, how do the alteration minerals, such as the titanium phase minerals, rutile, ilmenite, and titanite, in these barren and unmineralized zones, how do they change along strike? Is Jundee different or similar to other camps of similar temperature ranges? And the last one, fluid pathways, oxidized fluids. Can we really use anhydrite to map these oxidized pathways? And if not, you know, what other minerals can we use? And yeah, I guess I probably need to go and see if I can link anhydrite to stage 2B. So that's my little weekend's work. And that's the end.